We will start with our first keynote talk actually on the quantum computing domain. It will be on scalable methods and tools for very large quantum circuits. And our speaker for today is Alexandru Peller, who is an assistant professor in Aalto University, Finland. His research is on scalable methods for compilation and optimizations of fault-tolerant quantum circuits. He was the recipient of 2019-2020 Google Faculty Research Award. In 2020, he was the recipient of a Fulbright Senior Research Fellowship and also a visiting researcher at UT Dallas. Alexandru also organized a quantum resource estimation workshop along with ISCA every year. And I have been reading some of his papers, and we thought they have been doing wonderful work on some of the work on quantum resource estimation. So he will be a great speaker for this workshop. And with that, we like to introduce and welcome our Alexandru to present his talk. Alexandru, can you please share your slides?
Hi, hello. Thank you for inviting me. Let me see how I have to click here on a button.
So we want to also announce is that, so if any one of the attendees have any questions during the talk, you can type the questions and then Travis and I can ask the questions to our speakers. So please type your questions to the speakers in the chat window and we'll assemble the questions and ask to the speaker at the end of the talk.
Okay, so do you see my screen?
Yes, we do see your screen. Yes.
Do you hear me? Okay, so yes, so I'm grateful that you invited me to give this talk. I'm very happy to be able to talk about the things that been keeping me busy for the past years. Thank you for the very kind introduction. And indeed, I just started now being an assistant professor at Aalto University in Espoo. So Espoo is like a suburb of Helsinki. So kind of the Aalto University is in Helsinki, Finland. And what you see on this slide is the entrance to the computer science department building. So I'm trying to discuss about the things that I'm also continuing in Aalto. And that is scalable methods and tools for very large quantum circuits. So the motivation of the entire work is that at some point in time, people want to build a large-scale practical quantum computer. And although we are at the era of NISQ, the noise intermediate scale quantum, where we have, you see here on the left, some pictures of devices, maybe not the most up-to-date devices, but like these are very small devices with not even 100 qubits. And the idea is that quantum computing is expected to evolve into massively large mainframe-like machines by using quantum error correction and especially maybe co-designed quantum algorithms. And like from this NISQ era, there will be a transition, a gradual transition to these machines intermediated by design automation methods. And in this process, the computer architectures will be evolving. It is not known if the machines will be monolithical or distributed. And it's also not known if this will be actually like used for machine learning kind of approaches or like more like non-probabilistic methods. In any case, so the computer architecture approach is the one that is the basis to these machines. The design automation is the one that translates the algorithms to the architectures, and the error correction, the quantum error correction, is we could call it the technology that enables these large-scale practical quantum computers. And what you see on the right side of this slide is something people talk about quantum software stacks. On the next slide, I will also show you kind of a stack, but actually it's not really true that the software will operate in a stack. It's mostly like different components that are responsible for different aspects of the execution of these large-scale quantum circuits. And for example, you see here offline components, which are drawn blue, like these blue triangles, and red triangles, which are real-time components, in the sense that the offline components are you compile the circuit, the algorithm, before being executed, you protect it with error correction, and then you send it to this mainframe, like to this huge machine. And during its execution, the error correction is a dynamic process, and the machine has to be able to correct its errors. So this means it has to be able to adapt to events. So these circuits, these error corrected circuits, are mapped to the hardware, which is here below, and then the hardware devices, the hardware qubits, are interacted, entangled, measured, and based on these measurement results, this hardware interface sends the stream of measurement results to a tracking component, to an error correction tracking component that takes decisions. Did errors happen or not? Should I correct or not? Should I adapt the computation? And that's why it's a very dynamic process that is taking place, and these software components actually do not operate in a stack, but mostly in a distributed manner, where, for example, the tracking influences the optimization of the circuit, and the optimization of the circuit influences the mapping, and the mapping again is informed maybe by the tracking, because some information doesn't have to flow to some component but to the other. So it's a very complicated thing, and there are many proposals how to do it, but actually nobody has a working system because they don't have the working hardware. So it's ongoing research, and the scalability aspect of this entire software stack plays a very important role. Why? Well, these machines, because error correction is something that is definitely needed. So this means that the quantum computers, distributed or not, will operate on millions of physical qubits. So this means that even if the quantum algorithm expressed as a quantum circuit requires 100 qubits, the error correction and the entire redundancy that is included in these computations in order to achieve fault tolerance will take up to these millions. So here is actually the stack. For example, imagine that you have some kind of molecule or something of which you want to find some properties of it, and you use a quantum algorithm. And then you have a quantum circuit as an expression of this algorithm, error corrected, and then you have to prepare this algorithm to the specific architecture, error corrected or not. And this means you have to take the circuit and decompose its gates into gates which are elementary for the particular architecture. So this is an intermediate representation. But then you also have to map these things to the device, and here to the bottom you see the NISQ device, the Sycamore chip, the 54 qubit device. So yes, so because we do not have enough qubits, and we hope to operate on 100 or 200 qubits, optimization is still a must, because an even more aggressive optimization is required, because you cannot leave a computation to run for too long, so the circuit to be too deep, because at that point errors accumulate too much, and the results are indistinguishable from random noise. So yes, so most of the work that I will be discussing is an intense collaboration with UT Dallas, with Evan Dobbs and Joseph Friedman, and also with the University of Clausthal, the Technical University of Clausthal in Germany, with Umaru and Robert Basmajian. So I will kind of discuss the scalability aspects of these entire things, of this entire software tools that we have been working on, from the top to the bottom, to the mapping and so on. Everything is kind of motivated by this quantum resource estimation, where resource estimation is the question of how much time and how many physical qubits are necessary to execute an error-corrected quantum computation. So what you see here on the left is a grid of physical qubits arranged according to how these superconducting chips from Google are operating. So you have some qubits represented as crosses, and they interact nearest neighbor. And these are very specific because they are laid out like this because it's the surface code that is used for the fault tolerance. And you have to interact the qubits for a particular number of rounds in order to guarantee the fault tolerance in the surface code. So the question is, for how many times do you need to interact? How deep, how many rounds of error correction do you need? And what is the distance of the code? This meaning how big should be these lattices. So because as I mentioned, the input gate, the gate list of a quantum circuit is unerror corrected, and in the long term you want it to execute it error corrected. So this means what are the factors by which you have to multiply the resources from the initial circuit. So this is quantum resource estimation, and the hope is to take a circuit, for example, quantum chemistry, and find out as fast as possible to a rough but exact estimation of the number of qubits and the time necessary to achieve a certain fault tolerance threshold level and the number of qubits. Yes. So this is the tool we have called Gentiana, because this is a plant called Gentiana, and so the number of on the right, you will see now the number of physical qubits in the original circuit, and the question is, what is this minimum number of qubits necessary for error-corrected execution? For example, if you have 8 yellow physical qubits and you need to achieve fault tolerance, you need to repeat the syndrome extraction. So for how many times do you need to repeat the syndrome extraction? And you get some kind of a volume. In this case, an area, qubits multiplied with time. And the shades of blue represent the number of times you repeat some kind of procedure that achieves fault tolerance. And the question of these rough calculations is, can the costs be minimized? So what are the trade-offs? Trade-offs meaning that in this case we have 8 qubits used in 8 time steps. So if we express this area of the computation as time multiplied with qubits, it's like 64 units of space-time. Now the trade-off is, can we cut some qubits, save some qubits, but increase the execution time? So let's say that we do not have the hardware resources. We have only 6 qubits, but is it actually feasible for a particular computation to increase the execution time, to repeat the syndrome extraction such that the computation still succeeds by the same probability? So in this case, for example, we introduced 2 time steps, and we increased actually the execution time, but we saved on the hardware. So these are types of this tool allows us to calculate the resource estimations without actually laying out the circuit, but making only these space-time volume estimations and then playing with the properties of the error correcting code, in our case the surface code, and building scenarios and saying, okay, what happens if we have so many qubits with this error rate and the computation will increase by that factor? How long would it take? Is it actually feasible? And we get some plots where, for example, in the red region, it means no, it's not feasible. And in the green region, it says, yes, it's feasible for these parameter spaces. Or, for example, we increase the volume and say, oh, imagine that we have infinite time. Can we get the same computation on only 100 qubits? And we get some plots like this, like logarithmic. And this is like a good intuition of what could be achievable with some platform, hardware platform. But it's as I said, it's a rough estimate. And in order to also take into account some kind of optimizations that are possible at circuit level, we are looking now into using the ZX calculus. And this is a very interesting thing. It's a diagrammatic language that expresses circuits, and then the circuits can be transformed using a well-defined set of rules. So we combine the ZX calculus with our rough resource estimation engine, and we are interested in finding out rules about how the initial circuit properties can be transformed. That's why you see here the previous one was the Gentiana minima, and this is the Gentiana minore. We want to find out how the circuit properties transform the space-time volume and what the number of physical qubits and the execution times are accordingly. We call this ZX Keynesiana. Keynesiana is like we took the Python software, the Python framework. We compiled it to WebAssembly, and we are running it in the browser using WebAssembly, and we did the same for physics. So this is like really ongoing research where we want to really be able to allow the researchers to benchmark their quantum algorithms as fast as possible. And as exact as possible. But then, after having these rough estimates, you still have to compile the high-level circuit. So you still have to, for even finer details, for a better understanding of the things that you are doing, and we are talking here about circuits of thousands of qubits, unerror corrected, you still have to lay them out. So you get a rough estimate. You use Keynesiana, you use whatever tool you would like, and that's fast. But informed decisions still require the compilation of these circuits. And in general, as I mentioned on the previous slide, the gates and the qubits are not protected against errors, and you need to decompose your initial circuit into gates which are error correctable, assuming that you will have an error corrected machine. So this means that, for example, if you have very strange quantum gates of non-discrete rotations around the z-axis with some angle theta, you need to decompose this into using algorithms like Selinger's algorithm, and for an RZ theta, where, for example, this theta is pi over 128, you get a string of gates like S gates. This is a pi over 2 rotation, and T gates, pi over 4 rotation, and Hadamard gates. You get this huge string that approximates this rotation within some error. And then actually you notice that you had only one gate in your circuit, but then you get 100 gates which need error correction. So the depth of your circuit increases by a factor of 100 or something like that, huge. And for example, some high-level circuits are expressed with Toffoli gates, and then you need to decompose the Toffoli gates into also this Clifford+T gate set. Again, you see here the Hadamard gate, the CNOTs, and the T daggers, and so on. And here you have 6 T gates, and these are considered very expensive for the error correction. So the first step in this compilation procedure is to transform the input gate list to Clifford+T, and you may have very unpleasant surprises after you did this, due to how the number of qubits increases and the depth of the circuit increases. Anyhow, with collaborators, we started writing a tool called QUANTIFY, which we built on top of Google Circ, and we wanted to have some optimization features. So after doing this decomposition into Clifford+T, we wanted to flag some gates, and we wanted to in order to control how the optimization is executed, and only on those flagged gates should optimization be performed. And also we plugged QUANTIFY to the ZX Kentiana engine such that we can perform resource estimation. This is also ongoing. I mean, we are doing it, we are improving it at this stage, but we are close to that. And also, in the process of optimizing circuits, it's not obvious, but very often bugs appear in the Python scripts, in the circuit. Some circuit identities are applied wrong, and so on. So we have an invariant verification. So while optimizing the circuits, we perform some verifications that we are still correct. And this has proven very useful in the. I mean, some circuits you cannot do verify by hand. So this has proven very helpful when we wrote papers about very large circuits. QUANTIFY has this decomposition of multi-polarity, multi-controlled Toffoli gates into Toffoli gates. We use the standard decomposition. You see here an example. So it's like these gates that have multiple black dots and an XOR, and this can be decomposed into simpler Toffoli gates, where the Toffoli gate is this one that has only 2 black dots and the XOR. And this is like a canonical decomposition. There are newer ones when we are implementing them, but also the Toffoli gate the Toffoli gate. There is not a single Toffoli gate decomposition, and each one has its own advantages and disadvantages in terms of depths, space, number of qubits, and we support all. We also support relative phase Toffoli, so almost Toffoli gates, and we can also combine all of these Toffoli decompositions in a single circuit such that we can play now optimization games. So motivated by the error correction compilation of circuits, with respect, I will show later this thing, we have methods to commute the T gates through the CNOTs such that we achieve some kind of equal distribution of the T gates into the circuit such that we control the depths of the circuit. We can also push the T gates to the start of the circuit such that we do some kind of lattice surgery optimizations. And the classical things, cancel neighboring CNOTs, Hadamard gates, and so on. And as I mentioned, this is, even at the moment of speaking, the flag optimizer is something that not even Circ has. Yes, and we have a library of circuits that can be used for benchmark. We have state-of-the-art arithmetic circuits, adders, multipliers, QRAM. We have an implementation of Shor's algorithm, and so on. So, and we are still working on this. So, yes. So the QUANTIFY has these 4 aspects. The synthesis, as I mentioned, these circuits that get compiled and transpiled. The analysis and verification aspect, which is the foundation for the resource estimation, and then the optimizers, and these invariant checking optimizers. Yes, and then some these rewrite rules, template matching, Toffoli decompositions, and so on. Yeah, so this is like the architecture of QUANTIFY, and here you see, for example, a Toffoli gate decomposition. This gate here gets decomposed into the 4 ancilla the Toffoli gate decomposition. It has 4 ancillas, and the CNOTs here and the Hadamards are the one here to the right, and this is the decomposition. This is just an example, and this is an example of the Hadamard cancelling and CNOT cancelling. These are trivial examples. Anyway, so we also were interested in, because we really want these tools to be able to handle large circuits, and we mean large by very large circuits, thousands of qubits. And then we started benchmarking, and I have some slides later of the responsiveness and the memory utilization. So we are not interested in circuits of 10 qubits, of 15 qubits. We want circuits operating on 100,000 qubits. And you can see here, these curves are very discouraging because synthesis doesn't look very fast, but synthesis and optimization is even slower. For example, in less than a second, we can synthesize a 1,000 qubit circuit, but in less than a second, we can optimize with trivial optimization only 74 qubit circuits. And these are simple circuits, QRAM circuits, quantum RAM circuits, and this is like the log plot of the one that you've seen before. But I have at the closing slide of this presentation, I will discuss it a bit into more detail. But there is strong evidence actually that the reason behind these high execution times are the lack of specialized data structures that are in these quantum software frameworks, and we are using Circ. And the missing parallelization in the quantum software frameworks, because everything is written in Python and nobody's focusing on how do we write parallel optimizers, how do we do this and that, verifiers and so on and so forth. So it's a lot of work and a lot of research necessary to make large circuit compilation and optimization scalable. After the circuit has been compiled into this Clifford+T gate set and optimized and analyzed, one needs, for example, to generate the error-corrected circuit. And the latest, or whatever, the almost standard nowadays is a surface, are planar surface codes, and the way of implementing it is by lattice surgery. So lattice surgery, you have to imagine that you have these physical qubits on a grid, and this grid of physical qubits, you partition it into patches, and you see here the same grid partitioned into patches. And for example, in one patch in this pink one, for example, you prepare the states necessary for the T gates. And these are called A states, and it's a distillation procedure, meaning that multiple lower fidelity states are used in order to probabilistically obtain a higher fidelity A state. And these A states, nowadays also called T states, are required to implement the T gate in a teleported manner. And then you have other patches which are like the equivalent of ancilla qubits. These are the ancilla patches, like the yellow ones, and then the logical qubits are the logical patches, the logical qubit patches, the red ones. And this means that each patch on this represents a logical entity that is mapped to the physical hardware. And then these patches have two types of boundaries. This is because of how the surface code works. I have a typo, I'm sorry, operators. And depending on how these boundaries touch, different gates are implemented. So if the black boundaries touch, it's this kind of multi-body measurement, and if the non-black boundaries touch, it's this type of multi-body measurement. So you have like XX and ZZ parity checks, and touching these boundaries, merging them and splitting them are intrinsic operations in the lattice surgery. And then you can also do a kind of strange operation, which is called rotation. So when you take on the physical qubits, you apply some operations at the physical level, and then the boundaries rotate. So the black boundary will be not be top and down, but right and left. But it's not really sure how much space one needs to implement the rotation, and we take a very conservative approach here and use more than one patch to perform the rotation. So this is how it looks like. So for example, you map your circuit wires, qubits and gates to these lattice surgery operations and patches, and then as time evolves, these patches generate a pattern that looks like a 3D volume. And that's why you have this space-time volume representation of your computation. And then your qubits, the logical qubits, evolve in time, and then they touch, and wherever they touch, the merges and the splits are intermediated by these ancillas. And we have a tracker of the boundaries, and yeah, this is the distillation procedure. So this is the bounding box of the distillation procedure that happens in this pink, I think this is pink, magenta, region. And at the end, the output is located somewhere there, and then it's used for the multi-body measurement with this red qubit. And yes. So this is called an assembly. So this is another view of an assembly. Here time flows from left to right. And this is the distillation. And yes, the yellow segments are these multi-body measurements. And this is what one gets after compiling the circuit so the Clifford+T circuit into a surface code assembly. And we integrated it with OpenFermion, and we can get from OpenFermion the circuits. I mean, OpenFermion translates the circuits into Circ, and then these quantum chemistry circuits then are compiled to OpenSurgery, and then we can perform resource estimation using the Keynesiana engine. And we were interested, I mean, this is a talk about scalability, and we were interested in the scalability of this thing, and it seems to be quite scalable. It works. So as the compilation time grows linearly with the number of gates, which is very good. So the more gates you have a linear, it's not an even polynomial, it's actually linear, and it is actually constant with the number of qubits. And this is because we are using a very trivial, at this stage, a very trivial place and route mechanism, which is not optimized. But one can expect that at the moment when these assemblies will be expected to be more compact, more non-debuggable, because at this stage they are debuggable in the sense that I can visually recognize, this is this merge, this is this split, okay, this is this gate. So when they are more compact, things will look much worse. So there is ongoing research also in that direction at this stage too. Again, in QUANTIFY, we had an invariant checker, and in OpenSurgery, we have also some kind of checking mechanism, but we called it Corriere, because in the surface code, you have so-called correlation surfaces. And by tracking these correlation surfaces, these are the support of the error correction, kind of. And by tracking the support of the correlation surfaces, you determine if the circuit is correct. So the verification that we are performing is once the circuit has been compiled, we are expected to find some set of correlation surfaces. And if we are finding those, we are fine, and we define we consider the assembly correct. And this is actually tracking the correlation surfaces is not a complicated procedure. It's polynomial and works quite well even for large circuits. So yes, OpenSurgery is something that we worked on. It interacts with Circ, with Google Circ, with OpenFermion, and is like the next step after Keynesiana and QUANTIFY in order to get even more realistic resource estimations. And but still, there's a lot of work where we want to implement faster data structures for the lattice surgery, and the moment we will have the need for larger, much larger place and layouts, the place and route algorithms will that we are having at this stage will reach a limit, and then we need to invest some effort into making them faster. But then the question is, after laying these circuits, is how important is actually the T count? A lot of research is flowing into reducing the T count of a circuit. So because it's considered that the T gates are the expensive ones. And the question is, how important is it actually? Because if you look at this circuit, which is compiled, this is a braided surface code, and this is an adder. And the green boxes here are the distillations, and the qubits here are the red lines. And what you see here below this assembly is the quantum circuit that generated that assembly. And you see towards the end of the assembly, 1/3 of it here is empty. No distillations are executed because distilled states are only consumed. So this means that from the space-time volume of this entire computation, 1/3 of it actually is not used because distillations are, we consider them sequential, and there's no distillation executed. Then this means, well, is it actually important to reduce the T count, or is it important to schedule the T gates such that the depth of the circuit is used in a meaningful way? At this stage, this is the best we could get, and we couldn't reduce the depths more than that. So then the thing that we are interested is to control the distribution of these T states in the circuit, because this influences the depth of the assembly, the depth of the circuit, and so on. So is there actually a trade-off between the hardware and the time that can be explained through the layout of the topological assembly? And as you saw in Lattice, in OpenSurgery, we have this region where states are distilled, and then we assume that distilled states have to be kept in a buffer, which we call it like a queue, and then this buffer will be consumed by the implementation of the T gates on these red patches. And there's this general assumption that the worst case estimation of the T depths, so then is the T count. So this means that when people assume that the T gates are so important that the depth of the circuit is actually the T depths, which is approximated as the T count, but it's actually even worse than that. And there are some works which I'm not referring in this talk, but if one looks at this, it's discouraging. So actually, we have a model. This queue where we store distilled states, we have a model, and we model it as a queue, and we have a queuing model, and we assume that there is a certain arrival rate and consumption rate in this queue, and we want to find out what is the rate at which we can schedule distillations such that we minimize the storage and the depth of the circuit. And interestingly enough, it seems that for adders, for example, in this particular case, the Cuccaro adder, no buffering is necessary as long as the T gates are perfectly scheduled. This means that on average, 1 T gate per distillation execution, because distillation takes some time. And if you can guarantee that your T gates are consumed at a constant frequency, then you're fine. You do not need to store anything. So you do not increase the footprint of your computation, and you get the best possible depths. But if perfect scheduling is not possible, we need to determine this optimal buffer size. So yeah, so it's a procedure that one has to execute. And this procedure, this method is it's an iterative process for the optimal buffer size. We are using discrete time Markov chains for this distillery, and it has different stages with different capacities. We iterate the capacity, and then we see how the capacity of the queue influences the resulting depth of the circuit. And yeah, the worst case execution time is obtained for the most hardware efficient setting where there is no buffer. Or at least this is the expectation. So this is interesting because for some particular papers, you can limit the number of, you can force the number of gates, of T gates executed in parallel. Here we allow maximum 2 gates in parallel on this green plot, and here we allow at least 1 gate in parallel. And one sees, for example, that the number of T states, so this is the number of T gates in parallel in the circuit, and this is at so we have a queue that gets filled with distilled states, and the distillations are executed sequentially. And you see here the utilization of the queue. So at most we get 8 T states in this queue, in this pool, and afterwards this is the maximum, and afterwards it fluctuates until towards the end of the computation it's empty. Right, and this is at step 783. And if we allow only 1 T gate in parallel, the number of gates in the pool that one is expected to have reaches a plateau at 5. And it's the depth of the computation is 774. So it's really counterintuitive, but it seems that for certain circuits, T-gate parallelism is not something that one should necessarily follow. You can be very strict and say, I do not want parallel T-gates, because additional constraints on the layout will have surprising effects, such as reducing the total depth of the assembly. It's not that the T-count optimization seems to be necessary. It's actually the Clifford optimization that is important, and I will just leave this this slide as it is and not go into the details. It's very counterintuitive. People are focusing on optimizing these. It's expected that if one has fewer T gates, quantum computing will be possible, but it's not true. One has to optimize the cross-section of the computation, and the cross-section of the computation or of these assemblies are mostly Clifford. And if the T gates are scheduled correspondingly, everything is fine. Having now the assembly generated and analyzed, and the T gates and the distilleries controlled as needed, now the computation is sent to the hardware. And for this, one can use, for example, machine learning, because all the circuits that are all the circuit design methods that are used in the literature nowadays, they do not scale. Like for 100 qubits, and you have to have look-ahead strategies, and you have to know what parameters of my mapping strategy should I use, such that I get a good mapping. Yeah, so this is something that I want to talk about. For example, we have this circuit here. This is a small example of the circuit, and we want to execute it on the NISC. So this is not the assembly, but this is like the circuit, right? And initially, when people compile circuits, initially they have this placement. They say, okay, this circuit qubit will be on this hardware qubit, this one on that one, and then they schedule the gates, meaning that where should I execute a particular gate of my circuit on the device? So this is the initial placement, and for example, you see this qubit B goes on the hardware qubit Q0, this qubit A goes on Q1, and this ancilla 0 goes on Q3. But then the connectivity of the device, because it's restricted, and for example, in the Sycamore, you have nearest neighbor, but here you have whatever, this is a line. You need now to perform this 3-qubit gate, the Toffoli, and you do not have connectivity between Q1 and Q3. So qubit placement is actually really important, because where you place the qubits influences the number of swap gates that you have to perform during gate scheduling. So good placement, less swaps. This is kind of the deal, and the hope is to place with a parameterized look-ahead strategy. And then how do you find a good placement as fast as possible for large circuit? Because this is a combinatorial optimization problem. And so we came up with some kind of a Gaussian thing to select the most important gates from the circuit. So given a circuit, we have a Gaussian, and we learn for particular circuits patterns. We learn the parameters of this Gaussian, and we say, okay, actually this is the important part of the circuit, and we have to map we have to map the qubits such that this the cost of this region is optimized, and then hopefully we get an improved swap depths, total swap depths. So so for this Gaussian, we have to learn which part of the circuits is important. We have to select these parameter values. We place the qubits. We do exhaustive layouts, and then select the best layout and select the best parameter. So we train these parameters. And then when we meet a new circuit, which we haven't laid out until now, we know, oh, okay, oh, this circuit looks like that one, and we choose the parameters. And in order to train these parameter values, we used the QECO benchmarks from this paper. And we described also the circuits by their properties, depths, qubits, and we extracted this information with network X. And we were interested in how fast does our method work. So we really do not want to find the best parameters, because we are also interested in how fast the layout is performed. We have big circuits. We do not want to wait hours. No, and then we introduced some timeouts. And we counted the number of timeouts for these parameter ranges of the Gaussian and so on. And we reached a conclusion that actually within reasonable time, our method laid out the circuits actually very well compared with state-of-the-art tools. I'm actually the author of the tool that generated this red line, and this is like bad. Okay, let me explain this plot. This plot shows you the factor by which the depths, by which the compiled circuit has a larger depth to the original circuit. So this means the red line here, after compiling with this tool, you get a depth that is 12 times longer than of the original circuit. And then with the green line, which is TCAT, you get a depth which is at most 2 times deeper. And these are the, you also know the optimal depths, which you should expect. So you expect here 15, and you get by a factor of 2, this means 30, and by a factor of 12, it's, I don't know, 180. So this magenta line is our machine learned layout, and in all fairness, this plot doesn't. It shows that okay, we are a bit better than Qiskit, but worse than TCAT, but we are much faster. So this plot shows that the quality is there, but our compilation is much faster, is sub 1 second. Okay, so and now motivated by this thing of can we find the swap depths of a circuit as fast as possible without without laying out the circuit? Can we predict it? We started looking into into modeling the quantum circuits as queuing networks. So we have a scalable circuit analysis intermediated by queuing network models, and the problem is the following: we want to find out the swaps, the swap depths of a circuit, and maybe we optimize the circuit by hand. I haven't optimized I spent a lot of time to come up with a swap schedule for a particular multiplier, and you see here each time these links get pink, it means how the swaps are executed, how information flows from the bottom of this circuit to the top of the circuit. And this is a circuit that is 3D because we assume that we will use a quantum computing architecture where qubits have a 3D connectivity. So this is an example here, but this is the problem. We want to find out, given a circuit, given a layout, can we predict, can we give a lower bound of what is the best achievable swap depths? How much time should we waste trying to improve our circuit depths? So our approach is to create a stochastic model of the swap gates. And this allows us to consider the problem in terms of queuing networks. We analyze this network for this lower bound, and yes, we hope to apply this technique to look-ahead compilers. So for a 4-qubit, for a very simple multiplier at this stage, we just wanted the proof of concept, and we wanted to see if this really works. So we took a 4-qubit multiplier. This is the circuit you see here. It's a bunch of Toffoli gates and controlled additions. It's a right. So this Toffoli step has you see here, it's the swap count and the swap depth. So C is the number of swaps, and D is how many swap gates are in the longest chain between input and output. So it has this count and depths. But at each end of the circuit, there is a reset stage, and we have a constant depth of 5. The question is, should we look into even more aggressive optimization of this stage, or can we get a lower bound that confirms we are fine? And that's why we used this. And so this is the depth 5. You see here how the swaps are performed. Okay, so how the swaps are performed, the order of the swaps, whenever the edge here is pink, it means there's a swap performed between the qubits here that are the vertices, and the gray edges are the connectivity supported, for example, CNOTs in this architecture. So then queuing networks, a queuing network, like for the distilleries, is made up of nodes which service jobs. These networks are either open or closed. We use an open network, where in an open network, jobs entered by moving to a node are serviced and then move to another node. In a closed network, the jobs never leave the network. So it's like, I don't know, they stay in the network, just move between the nodes. Now, each node has a buffer capacity, and the nodes can be blocking. And if the buffer is full, then the node cannot service the next jobs, and then whatever. So those are waiting. So the biggest thing was to model the swap gate, right? So we want to find out how if we take a quantum circuit and we model it as a queuing network, then the thing is that these swaps are like jobs being sent between different queues. So modeling the swap gate, we have these non-boundary nodes, which are Markovian. The service process is Markovian. There is only one server at the node with a buffer capacity, buffer size of 1. First come, first serve. So that's why we have this complicated notation MM11 FCFS, and then when a node is occupied and not ready to swap, any job looking to the swap is blocked. So they have this blocking behavior. So is this simple model of the swap gate doing any working reasonably well? Yes, so here is the diagram. So this is the 3D circuit of the 4-bit multiplier, and this is the queuing network of it. You see here the arrivals at these lower queues here, and then the departures at the top antennas. And yeah, so we have this at each qubit, we have these jobs of capacity with a buffer capacity of 1. So we have a Markov chain and with transition probabilities, and we analyze these Markov chains, either empty or it goes to 1, 0 or blocking, whatever. We have the steady state probabilities. We simulate everything, and I'll just jump here to the results, and we find out, using our analysis tool, that the mean response time is 3.332. And we take this minimum response time as a lower bound on the swap depths. And we made a lot of simplifying assumptions. We used Little's law in order to reduce the computational complexity of all these things. We used we use a special kind of networks in order to simplify the steady state calculations. And okay, so, and even with all the simplifying assumptions, this mean response time means that actually a qubit that enters the arrival queue at the bottom takes around 3 point something, so sealing it 4 swaps to leave the circuit. Right? So our hand optimized swap depth was 5, but this is with a lot of simplifying assumptions, and we wanted the lower bound, and we got it. So this means that our optimization will only give minimal improvement and is not further optimization will only give minimal improvement and is not necessary. So we are now looking into really analyzing big circuits with these queuing networks and finding out the lower bounds on the swap depths. And finally, I want just to show you a slide on quantum software scalability. So with everything we did, with the tools that we wrote, we wanted to find out if we use the energy as the long-term cost of operating the classical hardware for optimizing quantum circuits. So let's say you have Shor's algorithm, it has 1 million qubits, you want to execute it, you need whatever, you need QRAM, you need the multipliers that are a sub-circuit in this Shor. So I said 1 million, but I wanted to say 10,000. You have 10,000 qubits, you have this multiplier, which is a sub-circuit that gets repeated multiple times. So you get this multiplier and you ask yourself, if I want to take this multiplier as a huge circuit, big, without considering other elements in it, but really only this multiplier, and I want to prepare it for error correction, this means move the T gates to the beginning, implement lattice surgery, get the things in this merge and split shape. How much energy, how much power would my classical computer require? And it's actually discouraging, because although we have polynomial complexity in all the things, the fact that the software is written in Python and we don't have special data structures and so on and so forth shows that we could end up, if things, making these worst case assumptions, we could end up consuming at least 1 gigawatt hour of classical energy just to compile Shor's algorithm for an error-corrected topological assembly. Of course, there are methods where you take like smaller sub-circuits, you do place and route and like that, but this just shows that there's a long way to scalable methods and tools for very large quantum circuits. And this is the conclusion of my talk. Thank you.
Thank you, Alexandru. Great talk. And we have a question from the audience. So I will read the question for you. The question is that, one question is that, what are important properties to verify quantum computing?
Oh, this is a very, this is a very broad question. This is a very broad question. To be honest, I don't know how to answer it. I mean, depends what you want to verify, right? So initially you want to check that you have a quantum algorithm that does something, and you want to make sure that that algorithm does really the thing that you expect it to do. So I think that's the correctness of the algorithm, but that falls outside of the scope of maybe my work. You know, I'm concerned more with the moment you have the algorithm and you assume it's correct and the theoreticians, they know what they did. You want to make sure that in the process of preparing the circuit and executing it, you are still doing things correctly. So this means you are still functionally correct. You have the gates in the correct order. You have things working as expected, But at the same time, you need to make sure that the error correction works, right? So because you make some strong assumptions about, well, these are the error rates, it's this thing, it's that thing, and you want to be sure that after everything has been executed, errors have not corrupted your state. So you, after this compilation and optimization procedures and checking and whatever, searching for patterns, that you really have to make sure that the error correction has not delivered something that is random junk. I think that's very difficult.
Right.
And maybe these are the three aspects, you know.
Right. Yeah, so maybe, you know what, actually, there is one question on the similar line. If there are any reference for verifying on the quantum computing, like verifying, I think there are some works, right? For probably we can later on send some pointers to the audience.
Yes,
right?
yes, there are quite a.
Okay, great. So the next question is that in that way, is there is an efficient way to detect the physical errors within or between the qubits when the quantum circuit is running? Like, so detect the physical error within or between the qubits when the quantum circuit is running.
Well, I mean, you need error correction. You need error correction, and most of the error correction schemes, so you do not care actually where errors happened as long as errors do not corrupt your state. And so maybe that's why you talk about equivalent errors. You know, like all errors are equivalent up to their effect on the logical state. So it is not possible to detect all errors, but what you care is finding out the most relevant ones that, or a marker of the relevant ones that corrupts your state.
Okay, and there is a similar question on the similar line. Is there a way to strengthen the qubit itself to make it more robust against error? Like, for example, there is a qubit, can we strengthen it such that it can tolerate errors?
Oh, I think this is like the question, like for example, in the like for transistors, right? You make bigger transistors, you do not have errors or something like that. I don't think it's that easy. There are different technologies of implementing qubits with different properties. Some are more prone to some errors and some to other types of errors, higher error rates, lower error rates. But this comes at the cost of speed. So the ones that are more tolerant to errors are slower. And the ones that are faster are also more faulty. So you cannot have, it seems very difficult to have both of the worlds.
Okay. And so another question is that, you know, right now, how big a quantum circuit can be implemented in hardware? Like, for example, right now, based on the literature or your experiences?
Okay, so based on the literature, I mean, the literature says that the biggest circuit that was executed is the supremacy circuit or whatever in that range, like 50 something qubit, but it's not doing anything meaningful in the sense of finding some cure to cancer or something. It's just a random circuit. So that's the biggest. But it was quite deep. And so deep that errors accumulated so high it was difficult to find the quantumness signature into that. It required a special protocol and so on and so forth. So if you really want to execute, like, I don't know, a Toffoli gate that has only a depth of, I don't know, 12 or something like that, it's quite challenging.
Actually, so I think that is that answer your question, how big a qubit circuit can be verified in simulations. And so, yeah, so right now, if you see, so I have one question from that domain. So you see that right now, when you are trying to map these circuits, let's say you have a Toffoli gate, and then Toffoli gate is finally decomposed into Clifford+T gate optimization, right? Now, you have seen some paper, like, for example, from like authors like Jidney and all those folks, they were trying to see if you can, rather than, let's say, if you have a function block like AND coming there, so you can do the optimizations and you can realize some of these AND functions in like a 4 T count. And similarly, when you are doing the reverse of that operation, you can realize this one. So so what is your work is interesting is that you're also looking into the lattices and all those things, right? Okay, so do you see that that types of optimization can help you in in your approaches when you're really looking for depth optimization or T count optimization or overall the Clifford plus optimization type approaches?
I think it's important, I think it's important, but I think it's overstated, definitely overstated, because I take the very conservative approach where I say hardware is so expensive that we have to do one distillation at a time. And this kind of simplifies everything. And at that stage, the Clifford optimization becomes horribly difficult. So it's important to reduce the number of T gates, but it's equally important to schedule the gates. But the measurements that they save on T gates, right? But the measurements that you have to do and waiting for the decoder to tell you, was there a logical error? How should I interpret the logical measure? That's equally difficult. So one has to take everything into account, what is your logical measurement time? And all of these things, it's not as easy. So it's great work that they are doing, and I'm also in that field, trying to save on T count. But for practical purposes, it's much more complex than this.
So I have a follow-up question to you. Let's say when when people publish the papers, then they look into some of the relevant literature and then they try to come out with those metrics, right? For example, let's say the metric is T count or T depth or whatever the metrics we can talk about, right? Now, do we think that because based on our experiences, the overall Clifford type of thing is also playing a big role? So do you see that people should, whenever they are trying to, let's say, list the T count or T depth or all those things, they should also list the Clifford depth and all those things? And what do you think is the overall metric should be defined? Like, how do we define the metric for optimization?
I think it's a volume metric that is important to have. It's a volume metric where you have some parameters, like the space-time volume, maybe, like where you have a cross-section, qubits. You make this cross-section also makes the assumption of how many parallel distillations do you have, right? And then you have the cross-section of the distillery. And then the depth is given by the best known rough estimate of the CNOT, of the T gate, and of those distributions. So like a space-time volume estimation of everything is like the fairest thing you could do.
Okay. Another question I have from that similar line, because there are many people from the conventional VLSI domain in the audiences, right? Okay. So, so one of the questions that is of interest is that, let's say when you're developing a EDA synthesis tool, like a synthesis tool for the NISQ machines, right? Okay. And then somebody like you guys are trying to optimize and compile like an EDA tool for the fault tolerant quantum computing, correct? Right. So I'm of the opinion, let's say after some time, let's say you transform from NISQ to fault tolerant, let's say after some time, right?
Yes.
Can somebody exploit like the EDA tool approach so that the work in the NISQ domain is also relevant to the fault tolerant, so that the work or the effort somebody put on the NISQ is also relevant to the FTQ?
Yes, that's a good question. That's a great. Yeah, I was also interested in this. The methods that you spend developing for something should be also for the other. And that's why I'm at this stage. I think people have not considered this option, but I think this is definitely something that should be considered. And the problems are so similar. For example, like the placement, and like the gate scheduling and so on. So I think there should be kind of a formalism that people will agree and saying, you know what, let's just take this, and also not only the formalism, but the benchmarks. I'd say, well, I've met reviewers or people that say, well, multipliers on NISQ, it's not feasible. It is not feasible, yes, but it's a very good benchmark because that multiplier is used in that circuit and the other circuit, right? Or the phase estimation, I don't know what, So there has to be like, there has to be a benchmarking suit and the parameters how to use this benchmarking suit such that NISQ and error-corrected compilation EDA tools can be, there can be a smoother transition. Yes.
Right. No, thank you actually, because see, we work on arithmetic circuit and it's good that you talk about multipliers and show that how it is useful. So, okay. So with that, actually, I think, do we have any questions from the audience? It is a large opportunity to ask any questions to our speaker. and after that we'll move to our regular talk session. So if any questions, please do send in the chat window, or you can ask, or you can, if there is any question, feel free to email our speaker also, right? Yeah. Okay. So with the interest of time, let's thank our speaker. Thank you, Alexandru. It was a wonderful